I was 5 and he was 6. We rode on horses made of sticks. He wore black and I wore white. He would always win the fight. Bang, bang, he shot me down. Bang, bang, I hit the ground. Bang, bang, that awful sound. Bang, bang, my baby shot me down. Seasons came and changed the time. When I grew up I called him mine. He would always laugh and say, remember when we used to play? Bang, bang, I shot you down. Bang, bang, you hit the ground. Bang, bang, that awful sound. Bang, bang, I used to shoot you down. Music played and people sang. Just for me the church bells rang. Now he's gone, I don't know why. And till this day sometimes I cry. He didn't even say goodbye. He didn't take the time to lie. Bang, bang, he shot me down. Bang, bang, I hit the ground. Bang, bang, that awful sound. Bang, bang, my baby shot me down.
So today we're probably going to finish up with trees and tree-based data structures. Just to review, again, the whole reason that we like trees is because they can give them more structure. A tree is an acyclic graph that we can go ahead and structure them in binary trees so that we have this parent-child relationship so that we can store data into them. And then finally, we made the observation that if they were essentially full binary trees with n elements, then their depth is going to be logarithmic. We then switched over to binary search trees in an attempt to give it even more structure so that we could search, so that we could keep keys in it, and everything to the left subtree is going to be less, and everything to the right subtree is going to be greater. However, we also observed that a binary search tree is not necessarily balanced, right? This is a binary search tree right here, right? 10, 20, 30, 40, ... 100, right? Its depth is not actually logarithmic. It's going to be linear, right? And so now we're back to square one where we've got a linked list. The solution to that, of course, is a balanced binary search tree, which goes beyond the scope of this course. But we will look at something that provides partial balance, right? And these are called heaps, okay? So what is a heap? Well, first of all, let's go ahead and think about where we've seen heaps before. And the context is going to be, we've seen stacks. When you think about a stack, what do you think of? You think very organized, right? A, B, C, one on top of the other. You can put stuff in, you can push things at one end, and then you pop them at the other end, right? It's very organized, one on top of the other. You don't want to, it's a restricted access data structure. You don't pull from the bottom. You don't insert arbitrarily in the middle or anything like that. It's very organized. Now that's a stack of stuff, right? It's a pile of stuff. But now when I say a heap, right? H-E-A-P, what comes to mind? kind of like a pile, a disorganized pile, right? Laundry, you know, you throw it on the heap of clothes, a heap of garbage, right? You're just collecting stuff in a pile somewhere. And if you were to throw something on top of this heap, what would happen to it? Well, it might end up where you threw it, or it might end up trickling down and end up down here, or it might end up down over here or something like that, or it might even fall all the way to the bottom here, right? That's what comes to mind when I'm thinking of a heap. Now, if you were to, just similar to a stack, if you were to pull something out of the bottom of the heap, you risk it collapsing, or at least, you know, some sort of avalanche or something like that. But if you took it off the top, right, then it's probably going to maintain its structure somehow, right? That's what I think of when I hear the word heap. Now, yeah, go ahead. Well, a stack is going to be organized. A heap is less organized, right? A heap is much larger. In the context of memory, when you've got a stack, you're talking about the program stack. So you've got function call on top of function call on top of function call. These are stack frames, right? So that they're breadcrumbs. I'm going to return back to where I called from, so I pop, 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 and it's very organized. A heap is less organized. It's just a pile of stuff, right? There is, but we need more structure. We need to describe that structure, right? So the structure that I'm going to describe is a heap. And again, the motivation is that binary search trees are not necessarily balanced. Let's go down here. There we go. Binary search trees in general could have a depth that is linear with respect to the number of elements in it, and therefore it kills all of our operations. Again, the solution is beyond the scope of this course. It is balanced binary search trees like AVL trees, red-black trees, 2-3 trees, et cetera, et cetera. But a heap gets us almost there, okay? A heap is a binary tree that has the following properties. One, it is full, right? Every child is present at every level except possibly the last, which is full to the left, right? And I'll visualize this here in a moment, right? It satisfies the heap property. Excuse me. Every key in each node is less than both of its children's keys, right? If the children exist. Of course, if it's a leaf, then it may not have children. It could have one child and not the other, etc. But that's the property. And this is referred to as a min heap. You can go ahead and flip this around and have what's called a max heap. It really doesn't matter because at the end of the day, you're probably using something like a comparator, like you're doing right now in your sorted list ADT, hopefully, for the full bonus. And so you have one heap implementation, and if you want to reverse it to become the max heap, you simply just reverse the comparator, right? So why are these two properties important? Well, the first property, the fullness property, guarantees that the depth of the heap is always order log n. So if our operations can be done with respect to the depth, here I'll even write it as d is equal to order log n, then they're going to be efficient, right? The heap property guarantees what? So let's take a look at a picture here of an actual heap and verify what the properties are. All right, so once again, it is full. Every node at every level is present except for the last level here. But the nodes are full to the left, right? It would be wrong if I put, say, some guy hanging off of here as the right child of 70. That is not a heap. It does not satisfy the fullness property. The second property is that it satisfies is the heap property. Take a look at every single node, right? 1, it is less than both of its children, 30 and 5 and 30. Now, don't read anything into 5 being over here and 30 like a normal binary search tree, because it's not a binary search tree. 5 is already greater than 1, right? And so it's a child. It's not a binary search tree. It's a heap. Take a look at 50. It is less than both of its children. Right? Like a binary search tree, we're not going to allow duplicates because I don't want to have to deal with that. You can always define a total ordering on your objects that you are sorting or that you're comparing, so that there's a tiebreaker, and it can be arbitrary. Okay. All right. So what does that second property get us? What's at the very top of the heap? The minimum. Right. The minimum is always guaranteed to be at the root. Right. So that's my second observation. The heap property guarantees that the minimum element is always at the root. Right? No other general conclusions can be made. Right? For example, we don't necessarily know where the maximum element is. Take a look at this particular example. Right? You could say, well, the maximum element is definitely going to be at the bottom somewhere, but you don't know if it's in the last tier or the last level or the second to last level. In this case, it's in the second to last level. I could add 100 here off of hanging off of 53, and now it's in the very last level. So it must be in one of those two bottom levels, but that's all you can determine. If you wanted to search through this tree to find the maximum, what are you going to do? Pre-order traversal, in-order traversal, post-order traversal, or a BFS. In other words, you're going to end up doing a linear search to find that element, or you're going to be doing a linear search to find any arbitrary element. So, from that perspective, this is not a general purpose data structure. Heaps are not general purpose data structures, right? They don't support CRUD. You can't just put stuff in, take stuff out, and update stuff and think that they're all going to be efficient. Instead, it is a restricted access data structure. Where have we seen that before? Stacks and queues. As long as you use them as a stack, as long as you use them as a queue, it is going to be efficient. As long as you use a heap as a heap, then it will be efficient. The two operations that it supports, two basic operations, are going to be get and remove the minimum element, right? And the second operation is add element. There we go. So you can put stuff in, but like a heap, right? You throw something on top of the heap, it rolls down to the bottom or rolls somewhere in the middle or something like that. You have no control over where it ends up, right? Or minimum control over where it ends up. The other operation is you can only pull off the top, right? So once again, it looks like this, right? That's, again, the idea that comes to mind when I think of a heap is a heap of garbage or a heap of laundry or something. You can go ahead and throw something on the top and then it'll end up somewhere down at the bottom, or it rolls all the way to the bottom or something like that. But you can only operate at the top here, because if you start pulling things out from the bottom, that heap is going to collapse, okay? All right, so how do we go about providing these two basic operations, okay? So let's start with the, add element. So let's think of ideas. How could I add an element here? Right?
Take left turns until it's null.
Okay, so give me an element to add here.
Let's go with 70.
70?
Oh, it's already at 71.
All right. 71. Okay. So you said just take left turns, so go over here, go over here, go over here, go over here, go over here. Yeah. So, okay, 71. Is that a heap now? Nope. It no longer satisfies the fullness property. Okay. Well, maybe I should start paying attention to the actual value here, right? What if I went right instead? Okay, well, it's got to be less than, or it's greater than 5, it's greater than 30. So maybe I'll go to the maximum, I'll go to the right. And I'll end up somewhere down here, but again, I have a gap. I don't want that. Think about the fullness property first. All right? We'll worry about the heap property second. Where could I put 71 here so that the fullness property is still satisfied? As the right child of 53, right? It is full. Right? We are satisfying the fullness property. What about the heap property? Is that satisfied? It is in this case, because you gave me 71. All right, so let's go ahead and change that so that it's something a little bit more interesting. Right? I don't know. Is 10 already? 10. Let's go ahead and add 10. There we go. So we'll do the same thing. I can go ahead and hang it off of over here. 10. There we go. And the fullness property is now satisfied. But is the heap property satisfied? No. 53 is greater than its child now, 10. So we just need to fix it. How do we go about fixing it? Swap. All right, once I fix that, then what do I have? Actually, let me switch over to this and just erase that, 10 and 53. 10, 53. All right, now with respect to those two nodes, the heap property is now satisfied. 10 is less than both of its children. It only has one child, but you get the idea. Now, is the heap property satisfied for all nodes? No. Okay, so keep going. I swap this. Right. And I have 10 and 50. 10 and 50. All right. Wonderful. Is the heap property now satisfied? Yeah. Right. All I had to do was make 1, 2 comparisons. Actually, 1, 2, 3 comparisons to stop the process, and only 2 swaps here. Okay. In the worst case, what would you end up having to do? Suppose, for example, that we didn't add 10. Instead, let's go ahead and reverse all this. Let's go ahead and add negative 10. Suppose that we'll support negative values here. Where is that going to end up? It's now the minimum, so it would end up all the way up here at negative 10 at the root, guaranteeing that the minimum is always at the root. And so we would end up making 1, 2, 3, 4 comparisons, 1, 2, 3, 4 swaps. We don't make another comparison because we stop once we're at the root. Right? So in the worst case, right, well, let's describe it first. Add element. Always insert at the next available spot in order to maintain the fullness property. Right? Then you heap, the process that I just did was called heapify. Right? You swap with parent elements until either the heap property is satisfied or you reach the root node. In any case, in any case, this is going to be the number of comparisons, swaps is what? Order what? D. Right? It's going to be relative to the depth. But what did we already say about the fullness property guaranteeing? D is going to be logarithmic. So this ends up being order log n. Awesome. Right? So that's efficient. Well, if we can get the other one to be efficient, then maybe we've got something cooking here. Right? What about remove element? Right, remove the minimum element. So first of all, save it off into a temp variable so that you can ultimately return it. Let's go ahead and go back to our diagram over here and look and see what that might look like. So I want to get the minimum here, so my temp variable will end up holding 1. And I end up removing it. The fullness property is no longer satisfied, right? I've got a gap here now. So my first thought is, okay, well, let's promote one of its children, right? What if we did that? 5. Actually, could we promote 30?
Just compare them to find the minimum.
There you go. We always promote, suppose that we always promote the minimum, right? So 5. All right, well, that leaves me with a gap right here. So continue downward. You said always go with the minimum. 50. All right. go with the minimum, which is 53. Right? Uh-oh. We got a gap, right? The fullness property is no longer satisfied. Let's go back to the drawing board. Literally the drawing board. Right? So I need to make sure that the fullness property is satisfied first, just like I did for the last operation. What element could I take and put all the way at the top here to ensure that the fullness property is satisfied? 63. Right? If I did that, then certainly the fullness property is still satisfied. Right? Is the heap property satisfied? Nope. So we do the exact same trick that we just did. What we do is we compare it to its two children, and yes, we do promote the minimum each time. Right? And so we swap this, and we end up with 63 and 5. So 63 and 5 are swapped. There we go. Right. Is the heap property satisfied yet? Nope. 63 is greater than both of its children. So we need to go ahead and swap that out with the minimum, 50 and 63. 50, 63. There we go. Okay. Is the heap property satisfied now? Nope. We still need to swap it with its minimum child, which is 53. At this point, you get the idea. 63, 53. 63, there we go. And you might need to swap it all the way down to the bottom. This is why I like that analogy of a heap, right? You throw stuff on the top or thereabouts, and sometimes it trickles down all the way to the bottom, right? Sometimes it trickles down somewhere in the middle, right? You have no control over that. The only thing that this is good for are these two basic restricted operations, right? So you save it off into a temporary variable. You promote the last element to the root, right? Then you heapify downward. Right? You swap with the minimum child, until the heap property is satisfied, or you reach a leaf node. Right? You stop when you get to the bottom. And it trickles all the way down to the bottom, and it's avalanched all the way down. Right? All right, in either case, guess what? In any case, the maximum number of comparisons, swaps, is D, right? The depth, which, as we've already observed, is going to be order logarithmic. In other words, as a restricted access data structure, both operations are efficient. Right? They're order log n. Right. There we go. Excellent. So we'll talk about an application of this in 1 second. Before we do that, I want to discuss how you would actually implement this in an actual program. You could go with a tree. And if you are interested, I encourage you to take a look at the CS2 book and read all about it, because at one point I figured this out, and usually authors of textbooks will say, well, you could do it with a tree, but it's better to do it over here. And I agree, but I thought, how would you do it with a tree? And so I derived all the mathematics that would be responsible of basically the key here is you need to have free access to the next available spot. You need to be able to jump to that spot in order to add it so that you can heapify afterwards. You need to be able to promote the last element, and so you basically need to find the next available spot and the last element. And just using some mathematics, you can figure that out starting at the root node. Should I go left, or should I go, is the next available spot or the last element in the left subtree or the right subtree? Right? And based on the number of elements in there, you can figure that out. Right? It's pretty easy mathematics, but I did write it up, and if you're interested, go ahead and read it. I'm going to show you the easy way that authors usually do. Okay. So This is a full binary tree. Right? What we're going to do is we're going to shove this back down into an array and come full circle. The way that I'm going to do that is I'm going to go ahead and establish this array. I'm not going to draw it all. Right? But here's my index 0. I'm going to burn that. I'm not even going to use it. Okay? Now what I'm going to do is I'm going to do basically a top to bottom, left to right enumeration of these nodes. Right? So 1, 5, 30, 50, 55, 40, 80, ... That's good enough. Right. By the way, what kind of an enumeration is that? What kind of a tree traversal algorithm does that look like? Breadth first search, BFS. Right. So I've burned the first index here. 1, 2, 3, 4, 5, 6, 7, 8, ... Right. And the root node is now at index 1. How does that help me? So the root node is going to be at index 1. Where is its left child? It's at index 2. Where is its right child? It's at index 3. Right? Let's go ahead and look at another one. Right? Let's not look at the root index, but let's look at, say, 5. It's at index what? 2. Now where is its left child? So index 5, or 5 is right here. Its left index, or left child is 50 and then 55. So 50 and 55, 4 and 5. All right? Let's look at 50. It's at index what? 4. So where is its left child? Where is its right child? I'm looking right here. 80, 60. I should have gone a little bit more. 53. There we go. 9, ... So its left child is at 80, or 8, sorry, and 9. Do you start to see a pattern here? Let's look at this more generally. If I've got a node here, it's got a parent, and it's got a left child, and it's got a right child. Right. If I say that this is at index, say, I, then where is its left child going to be? 2i. Where is its right child going to be? 2i plus 1, right next door. Right? Now, reverse that. Where is the parent going to be?
Depends on what it is, we usually calculate half, right?
Yeah, half of I. And then, well, you can't have 3 divided by 2 and have an index of 1.5. So, just take the floor, and it always works. Right? We know the floor? No? Okay, the floor is 3.5. Floor is going to be 3.
Rounding down is a big.
Rounding down, but also 3.99. Floor is going to be 3. Right? It does. You always truncation. Think of it like that. Right? But it's not truncation because it doesn't work for negative numbers. Right? Negative numbers, you would still go down to the next available integer. Okay.
So negative 3.9, go to negative 4.
3.9 or negative 3.9 floor would be the one integer down, so it'd be actually negative 4. Yep. So it's not truncation, it's the floor operator. Now, if you ignore negative values, because you never have negative values as indices, then yeah, you can go ahead and use truncation. Go to a language like Python, where you do have negative index values, you just write it back around, and now it don't work. But there you go. There's how you can do a tree with an array. Right? This only works because it is a full tree. If you had a gap here, right? For example, if you had, I don't know, say that you didn't have this stuff right here, right? You're going to have a huge gap there. In fact, you may end up having an exponentially sized gap in your implementation. And you don't want that, because now you are wasting an exponential amount of memory. So this only works because it's a heap and because a heap is full. If you are at a particular index, right? Index, say, I, then, too fat. You can jump to its left child by jumping to 2i. You can jump to its right child by going 2i plus 1. You can jump back to its parent using I divided by 2 floor. So in other words, now you can exploit random access to do all of this. Right? And it's really, really easy to implement this as far as an array is concerned. Does this solve our problem? Remember that to make this efficient, we always need to be able to have the next available spot, and we need to be able to grab that last element and promote it up to the root. Right? If I told you how many things are in here, how many things are in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Then where's the last element? What index is this at if n is equal to 17? 17. Right? So as long as I keep track of the size of the heap, I can jump to that location and give you the last one. Where's the next available spot to put something in there? N plus 1, 18. Right? So yes, all of our problems are solved if we have a simple array-based implementation. Okay? I'm not going to go through a full implementation, but I will mention that Java has one. Right? Java provides an efficient heap implementation using what's called we've seen it before, priority queue. Right, T, there we go. Let's go ahead and read all about that. I'm going to do it on a website. Here we go. Priority queue Java. Priority queue. Right? Well, it's a queue, right? You can put stuff in, you can take stuff out. Come on. And implementation note. This implementation provides an order log end time for the enqueuing and dequeuing methods, which are going to be offer and pull. Remove and add, of course, are just different behaviors of what happens when you try to remove from an empty queue or put into a full queue. Linear time for arbitrary removals. So if you want to treat this like a regular old list, then you're back at square one. You're going to have a linear time algorithm for this, for remove or contains or anything that basically has to look at the entire array in order to find what you're looking for. Let's come over here and let's go ahead and get rid of this demonstration. And let's go ahead and play around with it. Priority queue. And we'll do it for integers. Right. PQ is equal to new priority queue. I think it's not an interface, is it? Or was it? No, it's an actual queue. Right. So let's go ahead and bring this in. And I want to take a look, how did they do it? Did they do it with a tree and a bunch of nodes, or did they do it with an array? Guess what? An array. Right? So it keeps track of the size, it's got a comparator, a bunch of other bells and whistles over here too. Right? So let's go ahead and put stuff in. Right? I'm just going to go ahead and generate random numbers here. So for int I equals 0, I is less than 10, I plus plus. Right? Let's go ahead and create a randomizer. Random r is equal to new random. Random. Right? And int x is equal to r dot next int. We'll keep them small, at most 99. Right? And then what I'll do is I'll say pq dot offer, right? X. And let's also print it out. System.out.println enqueuing percent d dot 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 whoops dot 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 end line x, and I'll go ahead and change this to printf. There we go. So I'm putting stuff in. I NQ 29, 80, dot, 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 dot. Okay. Now let's go ahead and take a look at what the queue looks like after. System.out. Print ln pq. I wonder what it'll do. Oh, there we go. If you took that and put that into a picture of a tree, what would it look like? Let's come over here and create a new slide here. So what were they? I can make this smaller. There we go. All right, let's go ahead and draw them. 6. Then we've got 20. Then we've got duplicates. Right? Duplicates are allowed. 30, 66, 88, 85, 75, 49, and 66 again. Okay, so duplicates all over the place. All right. First of all, was that sorted? Is this in order? No, definitely not. Right? Because 6 is at the beginning, right? Because that's the minimum. But then we got 66 here, and then 66 at the end. But verify, just visually, is this a min heap? Yeah. Right? It's full. It's the last one is to the left, and every node is strictly less than both of its children. Okay. Less than or equal to, yes, because this is they do allow duplicates in this one. Right. Okay. What good is it? Let's go ahead and start taking stuff out. Right. While the heap pq dot is not empty, I'm just going to take things out and print them. Right. System.out.println print f%d space. In fact, comma. There we go. And I will say int y is equal to pq dot, what is it, pull? There we go. And y. There we go. So let's go ahead and take stuff out. All right? Different run, different random numbers. But when they come out, tell me what order they came out in. In other words, sorted. Hey, maybe there is an application there. All you need to do is what? Put stuff in, take stuff out. Now, if you remember way back to the beginning of the semester, I gave a couple of themes to this course, and one of those was a quote by a guy named Eric S. Raymond, who wrote this book, this series of essays on open source software, software development, philosophy of software development, right? And it's called The Cathedral and the Bazaar. The idea is that do good ideas, do good software, does good engineering come from the cathedral, right? The learned few, the good, the cream of the crop, and then they disseminate it to everybody, right? Or does it come from the bazaar, right? Where everybody collaborates and the best ideas bubble up to the top. And his idea was that it comes from the bazaar. That's the best way of doing things. Free and open source software, basically. So that was the aside there of the context. But one of his treatises, or one of his quotes was, smart data structures and dumb code are a lot better than the other way around. So if you remember back to Quicksort, really clever code, really smart code. It's got this partitioning that partitions in place around it, and then it does a recursion, right? And it achieves this order n log n algorithm, right? On average and in the best case. Really, really clever code. No data structures at all. It's just an array. Right? Now take a look at the opposite here. This is really dumb code. If I just take out my printing here, right? And I put stuff in and I take stuff out, right? Put stuff in, take stuff out. Right? That's dumb code. Right? All you're doing is putting it into a data structure and then taking it out again. But what magic happens at the end? It becomes sorted. So dumb code, smart data structure. This smart data structure is a min heap. Now, it's all for naught if we don't achieve the efficiency of quicksort. So let's understand this. Here's my heap sort algorithm. So my input is going to be a collection of elements, A1 through AN, right? And my output will be A sorted. Okay? All I'm going to do is initialize a min heap, right? For I running from 1 up to n, h dot nq a sub I. Right? My pseudocode is even going to be simpler than my Java code. For I running from 1 up to n, right? Then what I'll do is I'll output h dot get min. That's it. Put stuff in, take stuff out. Put stuff in, take stuff out. Now, is it efficient? This is going to be order 1 because you're just initializing a new empty array. What about this right here? This executes n times, right? What is the complexity of this line, though? Let's think about this. So iteration. The first iteration. What is the size of the heap? Careful. Is there anything in there first on the first iteration?
No.
Nope. So the size of the heap is going to be 0. So the number of comparisons
Oh.
to heapify
0.
is going to be, well, yeah, you'd say log 0, but is that defined? Careful.
No.
No. But that's a corner case. We would end up with just zero comparisons. Just create a new root, and that's it. Iteration 2, the size is now 1. How many comparisons do you do? Well, if you've got a root and you add one new child here, you need to know, do you do a swap or not? So in other words, you do 1 comparison. Third iteration, it's of size 2. You may end up having to do 1, 2 comparisons, I don't know, but log of the size of it, log base 2, dot, dot, dot. On the ith iteration, it's going to be of size I minus 1, and so you end up doing log of I minus 1 comparisons, dot, dot, dot. The last iteration is n. What is the size? N minus 1. And you end up doing a log of n minus 1 comparisons. So what is the grand total? So let's come over here. 1 plus, actually let me rewrite it so that it is a summation of I running from 1 up to n. Remember that we do start at 1 over here because we just burned this one. Right? So the size of the heap here, 1 up to n minus 1 of log I. Right? In other words, log of 1 plus log of 2 plus log of 3 plus dot, 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 log of n minus 1. Remind me of my log identities from high school. Log of A plus log of B is equal to
Log of A times B.
AB. Good. Now apply that to all of these. And what do you get?
Factorial of n minus 1.
Good. This is log of n minus 1 factorial. I don't like that minus 1. Let's go ahead and bump it up. This is less than or equal to log of n factorial. Factorials are huge, right? They're super exponential. But what happens to a super exponential when you take it down with a log?
It's less exponential.
Yep, it's less than. Oh, so here, what I'll do is I'll change this so that it's n to the n. So we can do another log identity. Right? This, do we understand this? That this thing is less than or equal to this thing. I just made it bigger. Right? Because instead of 1 times 2 times 3 times 4 times n minus 1 times n. I'm going n times n times n times n times, right? Now, what's that log identity? What happens when you've got an exponent in a logarithm? Put it out front. N log n. So, we just matched the performance of quicksort, merge sort, whatever, in the best case, in the average case, in the worst case. And we did it all with a smart data structure and nothing else. Right? This is called heap sort.
That is worst case scenario for the heap.
Yep, that's worst case, that's best case, that's average case. That's the case, period. There is no others.
Got it.
Right? I mean, you could get a best case scenario where it's already sorted, and then you put it in and it ends up being, well, it's still sorted, and then you dump it and it's still sorted, so you would end up with, the best case scenario could be that you only do order n comparisons.
A lot less swaps.
Yeah, a lot fewer swaps. And so this will be log of I, and so the entire thing right here will be order order n log n. Now, that was only the first phase. What about the second phase here? Guess what? It's the same thing, but in reverse. Why? Because as you take things out, the size of the heap goes down. So, this is also going to be, oops. Uh-oh. There we go. This is also going to be order n log n. Right? And consequently, the entire thing is going to be order n log n.
It would have been like 2n log n, but the 2
Yeah.
disappears into the
2 disappears into the ether. So that's where I like to end the course on bringing it all the way back around to Eric S. Raymond, that smart data structures and dumb code are a lot better than the other way around. Right? One of the things that you should get out of this course is, and we'll do a review on Tuesday or Thursday, depending on what we want to do. One of the things that you should get out of this course is, when you approach a problem, you start asking questions of, what objects should I create to model this problem? What data structures can I pull off the shelf so that I don't have to do any work, right? And I know that that data structure over there is appropriate for this application, but it's inappropriate for this application because then you're in the painter's paradox, remember? Right, where you're always starting at the beginning, and it's inefficient because it's a linked list. Right? And I can't tell you how many times I've seen code in the wild that is exactly that, and it never manifests itself because nobody really deals with big data in real life. Right? I've seen terrible loops that, well, I've demonstrated it before, but terrible loops that just iterate over it like a traditional for loop. And using a linked list, and it ends up being order n squared. Order n squared then makes it into, you know, as long as you're only ever dealing with like 1,000 records or something, nobody is ever going to care. Nobody's ever even going to notice. But the second that you have, say, 10,000 records, and you, wow, why is this so slow? What's going on here, right? Well, you need some data structure, data structure knowledge there. There is heap sort. That's it. Of course, now in your lab today, all you need to do is use the priority queue, and you're given a list of elements instead of just generating these random elements, and you need to put them back into the list. But that should be pretty easy.
And I assume you can change. So is this like all? Is this like a min heap? Like you can do the same thing for a max heap?
Yeah. Yeah. Well, what you would do is you, if you want it in reverse, you need a comparator for integers, and what I'll call it is int CMP reversed is equal to new comparator for integers, and then did I spell it right? Comparator, there we go. And let's go ahead and bring this in, add unimplemented methods here. And what I would end up doing is then I would end up reversing it. So O2 dot compare to O1, returning that. And then take this comparator, put it in your priority queue instead. Now watch, as before, the natural ordering was in increasing order. Now it's been in decreasing order. So this will take a priority queue. Just like with your list implementation this week, right? Hopefully you are doing it with a comparator. And if I wanted invoices in, I want them in reverse, right? I could go ahead and do that. Comparator dot, comparing, no, natural order. Can I take another comparator? Natural ordering dot reverse. There we go. I could have done this instead for integer foo. I can't do that? Oh, what?
We did something like this in the code, so.
Fine, foo. That's not safe though. So you're not able to do this, but I'll force it. This is a contravariance, but it's safe. It should be safe. Why are you not letting me do that?
You cast.
Yes, I can. It is comparable. Integers are comparable. Why are you not letting me do that? But whatever. I wonder, can int cmp rev dot reverse? Hey, there we go.
Which?
And then this is right back to square one. Natural. There we go. So, there's the reversed. Done. Oops.
No.
Oh, I'm not actually printing anything. I'm just printing the prior. All right, so go back to printing. System.out.println y. Just print. Make it pretty. There we go. There's reversed, and then back to natural would be reversing the reverse. There we go. There we go. So, all right. So we, next week we've got Tuesday and Thursday. Usually, I'll just do something short on Tuesday to wrap everything up, and on Thursday, I'll take a poll and see how many people would actually show up to lab. And if nobody's going to show up, then that's fine. If one person shows up, then I'll be here to help during lab. But otherwise, you can expect Tuesday would be the last lecture, last live stream too.
I forgot to ask, or I could check, when is assignment 8 due? Is it due at the finals week or?
Yeah, Friday next week. Sorry, not final. That's not finals week.
No,
that's what do you call it? Dead week?
Yeah,
Oh,
dead week.
what did you call it first?
Prep week.
Prep week. Okay, that sounds so much better. I guess I don't know.